Hello, Calculus 2, Chapter 6, Differential Equations. Check this out. So, we looked at this differential equation. We separate and integrate and solve this differential equation. And this is classic exponential growth. You know, the picture looks like this. Actually, it's exponential growth when k is positive. It could be exponential decay when k is negative. So we looked at that and did some word problems. They were when you do the word problems, you've already done the calculus to get from here to here. So then the word problems are very algebraic to find C and K and look at population growth. And they usually give you like 2 data points to find C and K. So we did all that. All right. So I don't know what to call that, exponential growth or decay and decay. Then that was in 6.2, by the way. Then we went to 6.3 and we just learned how to separate and integrate some DEs. But there was one word problem came up. It was this guy. This was called the Gompertz equation. So we solved this one. It was a little more tricky to integrate, but you still could separate and integrate. And you got here, which was a funny answer, this E function raised to this other E function. So it's kind of a trippy answer, and they called this the Gompertz model for exponential growth. And this one approached L, which was called the carrying capacity of the environment. So the population would grow toward this limit L. Let's just try something. If we took the limit as t goes to infinity, as t goes to infinity, we get e to the negative infinity. You know, e to the negative infinity is 0. 0 times c is 0. I've got e to the 0. E to the 0 is 1. And so I get L. So I just took the limit as t goes to infinity, and the answer was L in this model. So there was a couple good word problems. That was in 6.3. So when we moved to 6.4, I wanted to tell you about this model of population growth. And again, the idea is instead of unlimited growth, what happens is as we start growing, the rate of decay the k, which is the rate of growth, does not remain constant. If it remained constant, we have this. This is a constant k. This k is also constant, but if you consider it attached to this stuff, like I kind of consider this k attached to this stuff, then it's not remaining constant. And what happens is the rate of growth is declining, and we head toward this, and we have an inflection point actually, and we change concavity and we head toward this asymptote. Well, that's what happens here. The name of this is called the logistic model. So there's the differential equation. It's got an L in there again. And then the answer, I didn't teach you how to solve this one. I did teach you how to solve those two. The book has it in there, but in order to solve this, you need an integration technique from Chapter 8. I could teach it to you. They sort of try to teach it to you. Well, they don't. Anyway, they don't do a great job of teaching it to you. And so I don't want you to solve this DE. When we get to Chapter 8, I'll teach you how to do it. But so I don't want you to solve it, but there's the answer. So I'd give you the DE, maybe I'd give you the answer, and then I'd ask you to work with it. This is called the logistic model. It's interesting too. It acts like this. It acts like this. It approaches a carrying capacity called L. L is called the carrying capacity. Again, if you took the limit as t goes to infinity, take the limit as t goes to infinity, that's e to the negative infinity. That's a 0 times b. B's just some constant. That's a 1 underneath an L. I think we get L. As t goes to infinity, we approach L. And there's an inflection point where it changes, and that's kind of the critical point. I mean, you know, the rate of growth is getting steeper. The slope is getting steeper. The rate of growth of this population is getting steeper until it hits that inflection point, and then the rate of the population still grows toward this limit, but the rate at which it's growing begins to decline. The slope of the tangent line, or the rate at which it's growing, is less and less and less. And and it grows at a lesser rate. And that it hits its maximum rate of growth at that inflection point. And one thing I know about the logistic model is we're interested in finding that time. And that time always happens, watch this, it always happens at half the carrying capacity. In this logistic model, that inflection point, that maximum rate of growth, happens at half the carrying capacity, so half of L. I don't think that happens over here in the Gompertz model. There's an inflection point. I just don't think it's always at that halfway point. So this Gompertz model is a variation on the logistic model, but it's a little different. It's a different equation. Same sort of shape, but different shape, different equation. So let's do a problem. Let's do a problem. I'm going to get rid of these guys. So what I'm doing is I'm easing into 6-4, where I want you to know about the logistic model. But I don't even want you to solve it, because we can't solve it. What I want to do is just give you a problem. I want to say that there's a forest in Marion County. It has a carrying capacity of 800 is the carrying capacity. 800 coyotes. Just to keep with the alliteration here. The carrying capacity of coyotes is 800. And the differential equation is this. The differential equation is this. I'm making this up. 0.24y 1 minus y over 800. Notice I'm putting the 800. That's the carrying capacity there. That's the differential equation. I don't expect you to know how to solve it, so I tell you, here's the answer, kids. Y is 800 over 1 plus 39 e to the negative 0.24t. So I've given you the solution for this coyote population where they're living in this forest. It has a carrying capacity of 800. And then I ask these questions. What is the carrying capacity? Sorry, I should have had these up here. Part B, what is the initial population? The initial population of coyotes. Part C, what is the population in 10 years? And there's one more question, part D. Okay, this is 6-4, the logistic model, and there's one more question, part D. When is the coyote population growing at the greatest rate? Growing at the greatest rate. I'm sorry for my penmanship. When is that's why I'm reading it to you. When is the coyote population growing at the greatest rate? All right, so these are easy questions. First of all, what's the carrying capacity? Duh, it's that 800. You know, even if I didn't tell you that, I might not tell you that. You should say, oh, the carrying capacity is the limit as t goes to infinity. You could take the limit as t goes to infinity and realize that as t goes to infinity, e to the negative infinity is a 0. 0 times 39 is 0. We end up with 800. 800 coyotes. And it's about the limit as t goes to infinity. What is the initial population? And hopefully you realize what that means. That's the population when t is 0. And, you know, maybe I could have defined that as some year, 2015 or something like that. But anyway, I didn't. But t equals 0 is going to give me the initial population. I'll plug in a 0. E to the 0 is a 1 times 39. 39 plus 1 is 40. 800 divided by 40. 800 divided by 40. Is that 20? I think it's 20. The initial population was 20 coyotes. Their population is growing. Their population is growing. What is the population in 10 years? Plug in a 10. Pick up a calculator, plug in a 10, do the math, or I'll do it right over here. It's 800 over 1 plus 39 e to the negative 0.24 times 10. You just got to use your calculator correctly, divide correctly. Let me try it. Let me try it here. 1 plus 39 e raised to the negative 0.24 times 10. That's a number. 800 divided by that number, it's about 4.53. 800 divided by that number is 176. Wow. 0.3 coyotes. 176.3 coyotes in 10 years. There's a lot of farms around. Maybe some of them are getting shot. Who knows? This is their, I'm sorry about that. This is their, this is the rate of growth of this population of coyotes in this forest. Anyway, easy algebraic questions, man. Easy. There's no calculus to this. The calculus was behind the scenes. I'm sorry. This is a good question, though. When is the coyote population growing at the greatest rate? So I previewed that idea. It's growing at the greatest rate at the inflection point. That's a calculus idea. So you might think, shit, I got to go find the inflection point. So to find this inflection point, you have to take the second derivative and set it equal to 0. It'd be nice to try to do that. Take the first derivative, isn't too bad. The second derivative is a bit of a challenge. I think I made my students do that in Cal 1. And then you set it equal to 0 and look for that inflection point. But we can do it easier. We can do it with algebra because of this given information. I'm looking for when that happens. I'm looking for the t value, and I already told you it happens when the y value is half the carrying capacity. So we take this equation, 800 over 1 plus 39 e to the negative 0.24t, and we set it equal to 400. We set it equal to half, and we try to find that time t, and we do algebra. So it's easy. Let's do it. Let's see what we get. I'm going to move some of these questions. I'm sorry. I'm going to move these so I can do a little math. You know, I'm going to multiply by this denominator, so I get 1 plus 39 e to the negative 0.24t times the 400 equals the 800. Of course, now what am I going to do? Of course, I'm going to divide by the 400. That'll give me a 2. 1 plus 39 equals 2 when you divide by 400. Subtract the 1, it's a 1. Divide by 39, it's a 39, equals e to the negative 0.24t. You follow that? And take the log of both sides. The natural log of both sides, negative 0.24t equals the natural log of 1/39. Divide by that little decimal and you'll get t. T is the natural log of 1/39 divided by that negative 0.24. And I'd pick up a calculator and try to find that time. You know, in 10, what we're trying to find when it's 400 coyotes, okay. Yeah, in 10 years it was, I just erased that, in 10 years it was 176 coyotes. Anyway, let's see what this is. The natural log of 1/39 divided by negative 0.24 comes out to be a positive number. That's a negative number, that's a negative, but it comes out positive 15.26 years. So from year 0, whatever that was, in 15 years we've reached this half the carrying capacity. And from this point on, the rate of increase begins to decrease. Did I say that right? The rate of increase begins to decrease. The population still increases toward 800. All right, you can do some homework. Now listen, I feel like I'm at the end of this chapter 6, differential equations. There is a section 6.5 and a section 6.6, but again, I've tried to tell you there's a whole course called differential equations, so I want to save some stuff for when I teach you the course, differential equations. I'm anxious to get to chapter 7, start some different stuff, new topic in Cal 2. So I've got this abridged version of chapter 6 that I try to teach, and I feel like we're about at the end of it. I might want to do some more homework problems. I could take requests. If you got any requests, let me know. All right, thank you.